let us look a little bit further at quantum number theory. So we've already looked at the Bohr model of an atom and the idea that as you get farther and farther from the nucleus, your electrons get more and more energetic. Now, while this is a wonderful model for us to start with, it doesn't fully help us understand all the beautiful properties of electrons. So 3 people, Heisenberg, de Broglie, and Schrödinger, all helped us kind of learn a little bit more and develop more of this quantum theory that we're beginning to kind of get the tip of the iceberg of in this chapter. And so the idea is twofold. Particles, electrons behave both as a particle and as a wave. And so they really kind of move around and flow like a wave, but then they're also a individual entity. And so because of this, you can't know both the position and the momentum. This could be for a baseball traveling through from the pitcher to the catcher. It could be an electron. Basically, it's more pronounced, though, for objects that are moving really, really, really fast, like electrons. And so the idea is if you know its exact position with time, you can't really know the momentum. And if you know its momentum, then you can't really understand its position. And so with the Bohr model, that starts to fall because it's not like electrons are traveling in perfect circles, because in that case, you would be able to tell both the position and the momentum at any given time. Instead, we're going to get these like probability diagrams like you see on the right, where you have an idea of where the electron exists, but you don't know its exact position with a whole lot of certainty. And so if you look kind of at the bottom right-hand corner, this distance from a nucleus R, the radial probability, that's the idea that most of the electrons are kind of be some perfect distance there from the nucleus, but they can get closer to the nucleus, they can get a little further. The line diagram is showing you as you start at the nucleus and you kind of proceed outward in a straight direction. And so these are all just ideas that help us think about electrons existing as probabilities. I know the electron is probably in the spherical shape somewhere around the nucleus. I know an electron is somewhere in this dumbbell-looking shape, whatever the shape may be. Or I can know, oh, it's probably up to this distance away from the nucleus because its energy level is a 2 or a 4 or a 6 or whatever it is. But we don't know a whole lot with a lot of certainty. And so as we're expanding this quantum theory that we looked at in previous videos, we're going to focus on 2 of the 4 quantum numbers and kind of think through what's happening and why, what is the shape, what's the probability shape for where the electron resides. So the first 2 quantum numbers that we're looking at are a principal quantum number and the angular momentum quantum number. The idea is that in any given atom, quantum numbers are an attempt to describe the location of the electrons around the nucleus. So your principal quantum number, just as we talked about before, has that symbol N, and that's going to tell you how far away you are or how much energy you are in the space around the nucleus. It'll tell you the size, how far you are, and then just how much energy. So an N equals 1 is less than an N equals 2, and so on and so forth. A subshell now is a new term, and it's going to tell us the shape of that orbital. Its symbol is an angular momentum is a little L, and it's actually kind of a cursive L. And so with each of those, we're going to talk about 4 different types of subshells, an S, a P, a D, and an F. And each of these subshells have a certain number of orbitals contained within them. And the S subshell gets a 0 assigned to it, a P is a 1, a D is a 2, and an F is a 3. And we'll learn more about this as we keep going. So just kind of at this moment, think about the principal quantum number. That's your energy that we've seen in previous videos. And then this new term is subshells, and that's going to tell us about the shape of the orbital that the electron resides in. So our first energy level, N equals 1, has a subshell of an S. And so an S is simply a spherical subshell. It has orbitals that are spherical. What is an orbital now? An orbital is a subclassification of subshells. So every subshell has some number of orbitals. But the important part here is that orbitals can maximally hold 2 electrons. Okay, you can't put any more in there. You can put less than, you can put 0, 1, or 2, but you cannot put 3 or bad things would happen. All right, so any orbital contains 2 electrons. An S subshell always contains 1 orbital. Okay, and that's pretty important. The S subshells are spherical orbitals, and you can have them any size. So if you have a 1s, that is an energy level of 1 with the shape of an S, which is a sphere. If you have a 2s, It's a shape of an S, which is a sphere still, but it's just a bigger sphere. And so remember, these are just electron densities. I'm not saying they reside on the outer part of the ball. I'm not saying they only are inside the ball. They are existing within that region that is defined by the parameters of the shape of a sphere. All right, so what about an n equals 2 then? So n equals 2, it has the 2s that we talked about before. So it's got those spheres, okay? But it also has a p. So it has s subshell and a p subshell. So what is this p subshell? Before we go any further, I want to note that look at the size comparison, a 1s versus a 2s. So the 1s is smaller, it's less energetic. The 2s requires more energy for an electron to reside within it. All right, so the only thing difference between a 1 and a 2 is energy. The S correlates to the shape of that subshell. So then what about the p? The p orbitals here, you can see there's 3 of them. So with any p, you're going to have 3 orbitals. So p is the subshell, and then the individual orbitals are the different orbitals within the p. So for any s subshell, you have 1 orbital. For any p, you have 3 orbitals. But it's still true that only 2 electrons can reside in any one orbital. And we're going to practice this so much, this is going to come to second nature to you. Okay? So that means that in any p subshell, you can fit 6 electrons because 2 electrons will fit in this one. 2 electrons will fit here. And my handwriting is really bad today. And so you'll have 2, 4, 6. You'll have 6 electrons that can reside total within the p subshell. And if you'll notice, what's the difference between each p? They all have those orbital shapes. It's just where along what axis does the orbital reside. So one's the x, y, and then a third is the z. But you have 6 electrons within the 2p subshell. You have 2 electrons in every single orbital. And then within the energy level of 2, you actually have 2 subshells for a total of 8 electrons. 2 within the 2s, 6 within the 2p. All right, what about n equals 3? Within an n equals 3 energy level, you have an s, a p, and a d subshell. So it's the same types of shapes as before. Your 3s looks just like the 1s and the 2s. It's just bigger, so it's more energetic. The 3p looks just like the 2p. It's just more energetic. So at this moment, you have 2 electrons in your 3s. You could have up to 6 electrons in your 3p. And then what about your d? So it is going to go, your s has 1 orbital, your p has 3 orbitals, your d has 5, and then your next one, your f has 7. So it's going to be odd numbers. All right. But this is kind of a summary of them all. Within the n equals 3 energy level, you have 3 subshells, your s, your p, and your d. Okay, so those are your 3 subshells. Your s can hold 1 orbital, your p can hold 3 orbitals, and your d can hold 5 orbitals, which means your s can hold 2 electrons, your p can hold 6 electrons, and your d can hold 5 times 2, which is 10 electrons. So what does the d look like? I'm glad you asked. I call them flowers or clovers. So there are 4 that kind of have that clover or flower shape, and then that last one, I kind of call it a dumbbell with a donut around it. That's its shape. When I get to F, I'm not even going to attempt to tell you what I call those, okay? But they get more complicated because they're more energetic. The P is more energetic than the S, the D is more energetic than the P, and so on and so forth. But all of these, so that N equals 3, your energy level is going to be relatively larger than the N equals 2. That means a 3S is greater than a 2S, a 3P is greater than a 2p, and then your 3d is your first d subshell anyway. There's no other d's lower than it. So that means if your energy level is 3, you're going to have 3 subshells. You're going to have an s, a p, and a d. You're going to have 1 orbital in your s, 3 orbitals in your p, 5 orbitals in your d, as mentioned before. All right, then, what about our n equals 4? Well, these are the crazy shapes I was telling you about. You're going to have 7 possible shapes. They look all kinds of crazy, so I typically don't say, hey, what's the shape of an F? They look like this. This is kind of hard to describe in words. You got 4 kind of paint splatters, maybe some double donut dumbbells up top, however you want to describe them, but they're just kind of crazy. But the idea still exists that each orbital can only hold 2 electrons. So the F is a subshell, and it refers to the shape. Each orbital, which there's 7 of them, can hold 2 electrons. So the F subshell can hold a total of 7 times 2 or 14 electrons. And so this is still true here for summary, is that if your shell is n equals 4, you're going to have 4 of these subshells. S, P, D, and F are their names. S holds one orbital holding 2 electrons. The P is 3 orbitals holding 2 electrons each for a total of 6 electrons. The D, there are 5 orbitals, each holding 2 electrons, which means you have 10 electrons within the D subshell. The F has 7 orbitals with 2 electrons each, giving you 14 electrons total. So add all that up and you can tell me how many electrons are in the total. Our total could be contained within an n equals 4 shell. Okay, but the important thing to think about here is your vocabulary. So a lot of this is identifying vocabulary. What's the principal quantum number? It's this N, it's your energy level. What is your subshells? Your subshells can be identified by the letters S, P, D, or F. Those letters just identify the shape of the orbitals that are contained within the subshells. The orbitals are the specific, what plane is it on, which shape that correlate with each subshell. And then the number of orbitals are here, and you have 2 electrons in every single orbital. So that's kind of a summary. We're going to practice with this later, just kind of practice thinking through how do we figure out where these electrons are, how does this relate to anything. So while this is more of a vocabulary building PowerPoint, not a practice. So we're not applying things right now, we're building our vocabulary and making sure we understand the concepts of shell, subshell, and orbitals. And then we'll be able to apply this to the periodic table.